I don't start that.
All right.
Can we use this mic?
Say which microphone would you like me to use?
The
Wireless?
collar one. So it will pick up both zoom and.
That's it. It's the single device. And she was learning one hand. That's not the only way. Focus. Focus. So I think this is a good place to sit.
Yeah, sure.
So we have to clap.
So yeah. Is this a good place to sit for him to for the recording? Yeah, you can. You want to
Or should I move over there?
closer to the edge? That would also be. That would be nicer. If it doesn't change things. Yeah.
Sit down there.
इथे बस रे
I'm right in there, so I can sit.
मध्ये चालेल का ते इथे झालं हा हा चालेल वन साइड बघा
So कुठं त्याला एक
in the audience thank you for coming you can sit on thousand that's always matter so well, the rain some people are getting delayed habits just maybe take 5 more minutes you can have you don't be chill. Hey, where is the remote? Hi, sir. It also depends on yes.
it's a little slow to change.
Yes, I put it on the screen. Okay. Okay. Yes. Okay. I want to catch something, some outside, take it a nap. You start in 5 minutes or so. Right, right. Evening. We can have tea hours then come. That's the way we'll be starting in 5 minutes. Yeah. The rain is causing some traffic issues just outside the university. Oh, no problem. See, these people would have missed some few minutes. Yeah.
Yes.
Next topic.
42.
This is good. Sorry?
Yesterday we were playing with observatory.
Yes. Up on the rooftop. Oh yes, it was.
We were about to like come and I was on the way and it was
It was a great time. It was fun to meet someone, and I'm very impressed with your observatory. How you built everything yourself, every piece, every computer, every wire, test. It's very impressive. Is everybody good? Good, good. Yes.
because people are connected.
It's so fancy. It's very sticker getting insulated. I'm going to ask everybody to try and move forward, please, to be more friendlier for the speaker. Yes. I'm very nice. I don't bite. Guys, don't go back. Please take the seats in the front first. That's it. Next one. Yes. Good evening, everyone. Welcome to Ayuga, place where we always take efforts to connect scientific research with all those who are interested in it. And in particular, we have been for many decades taking efforts to inspire and encourage amateur astronomy all over India. Because as you will know, that Professor Jay Narikar, who was a founder director, he's been also a big proponent of public outreach
and hence there's a nice combination of all such activities that happen regularly in Ayuka. So today we are organizing this special event, in particular for amateur astronomers or those who are interested in getting into some serious astronomy. Maybe since I see many youngsters here, maybe you'll follow it up later in your life as professional astronomers. But that doesn't matter. At this moment, we are all amateurs here in this room, either starting off or trying to find that balance between our regular life and the life and the part in which we are astronomers.
Mhm.
So we have a special amateur astronomer visiting Ayuka this week, Mr. Ted Blank here. So Ted is a perfect example of what I just said. So as far as I know, he's got many hats, but his profession was in the IT industry, and he has worked for more than 35 years with big companies like IBM, Oracle, etc. That's his day job. And as he says, he also stays up nights, evenings and nights, looking up at the sky, and not just looking up and enjoying it, but also making very serious observations of it. So over many years, he has gained great experience in the objects which are part of our solar system. In particular, he is interested in the timing of occultations, which are timing and recording of occultations, which are basically some object hiding another bright object in the background. So maybe you can call a solar eclipse as an occultation, but that's not the occultation he likes. He likes the challenge. Everybody's seen a solar eclipse maybe, but we are today through him also going to see other eclipses happening in the sky and how amazingly useful they can be as a very simple concept, but with great fruitfulness. So he has also been the NASA Solar System Ambassador since 2010. In fact, as far as I know, I think the NASA Solar System website also was built under your supervision. And
No, but I'm there. I'm on the website.
you're on the website.
That's all.
Yeah, so lovely to have you here. He's been the past president of the New Hampshire Astronomical Society. And of course, all through his life, he has enjoyed sharing his knowledge on any topic related to astronomy and the solar system. So it's a great pleasure to welcome him here. And it's a great pleasure to have you all here. The plan for today is, of course, to start with an introductory talk by Ted. And then we'll have discussions. You can have question answers generally to understand the topic further. We can also have discussions on how to take this field of occultation observations and recording more seriously, and how we ourselves can immediately get into that. There are several amateur groups in Pune, which is a very lucky city that way. So if you are associated with a group, there are many activities which can be done by amateur astronomy organizations as a group with their small telescopes and very basic instruments. So that also can be discussed, and hopefully at the end we probably will have some tie-ups and action plans coming. So thank you. I'll immediately pass on the floor to Ted.
Thank you. Thank you, Spirit. Hello, good evening, everyone. Is it okay? Can you hear me okay?
Yes.
Great, thank you. All right. Well, as you said, I'm Ted Blank. Recently arrived in India for the first time 2 days ago. So I'm still a little tired, but I think it's working out okay. Today's talk is going to be about what we call citizen science opportunities in asteroid measurements and occultations. You are all interested in astronomy to some degree, and occultation measurements, to me, was an exciting way to become involved in gathering scientific data without having to become a professional astronomer. This is one of many ways that amateur scientists and citizens can make real contributions to solar system science without necessarily being a full-time astronomer, getting a PhD, having a job at IUCA or anywhere else. But as a member of a worldwide group of amateur citizen scientists working together and also taking advantage of many of the software tools that our group provides that will allow you to know when one of these events will be visible from wherever you live and what time and where you would have to put yourself and your telescope in order to observe the event. These free tools available on the web will encourage your cooperation, and they also allow people to collaborate by telling everyone else who is going to observe the same event where you will be on Earth, so that, as you'll see in the presentation, having multiple observers spread out across Earth gives us the opportunity to learn more about this asteroid than if everyone was in the same place. So the only bad part about occultation science is you never get to do it with your friends next to you. They're always somewhere else. You're communicating by text message, you're communicating by phone, we're communicating by internet. But the idea is to spread out across the globe in such a way that we can cooperate. And you'll notice that some of these events are visible on different continents as well. So the shadow of an asteroid might cross the Earth, be visible in India, and 20 minutes later be visible in North America. And amateur observers on both continents are cooperating on the same scientific investigation at the same time. So I'll try to take you through this whole process and explain to you how it works, what the value is, and so on. So I'll start by just giving you a very quick overview of this idea called an occultation. We start with a star out in space, many light years away, and much closer to us here on Earth would be an asteroid in the asteroid belt, somewhere between the orbits of Mars and Jupiter. So we're talking about local compared to these distant stars. So if you can imagine that as the asteroid moves through space, imagine a single star shining light on the asteroid and shining light on Earth, but the asteroid is casting a shadow on our planet Earth from a single star, a very tiny source of light. Now, it's actually casting many shadows on Earth because every star puts a shadow of the asteroid somewhere else on the planet. So if you are in the right place, as you might see on this diagram here, our shadow is going to cross Earth from North America all the way over here to Africa, across the ocean. And we have 5 observers identified here as A, B, C, D, and E. Observer A is positioned just outside the shadow of the asteroid, and observer E is just south of the shadow of the asteroid. But the 3 observers, B, C, and D, will actually see the star disappear behind the asteroid if they're looking at the right star at the right time. And the weather cooperates, and it's nighttime, and there's no clouds, so lots of things can go wrong. But if everything goes right, we begin to get some information. The other piece of information that's important to understand is that the star is so far away that the light rays coming from the star are parallel when they reach us here on Earth. Now, if I were to take a flashlight and hold my hand and make a shadow, the shadow on the wall would be much larger than my hand because the light rays would be going out at an angle. But if you could take the flashlight and take it very far away, then the shadow of my hand would be the same size as my hand. This is what happens with asteroid occultations. The star is so far away that the shadow on Earth is exactly the same shape and size as the sky plane image of the asteroid at that moment. So when we measure the shadow as being 10 kilometers wide, that tells us the asteroid is 10 kilometers wide. And we're talking about measuring the diameter of an asteroid to within plus or minus 1 kilometer at 400 million kilometers away. This is a level of accuracy that cannot be achieved in any other way. And we can do it here on Earth with amateur equipment, small cameras, people without advanced degrees, a camera, a recording device, a telescope, a battery, and jump in your car, drive a few miles, point it at a star, and you make an incredibly accurate measurement of information about the asteroid, not only its physical characteristics, but also its orbital parameters, because we also measure the time that the star disappears. And that's the most important part, because that measurement of the time that the asteroid blocks the star tells us exactly where the asteroid is at that millisecond. And that allows us to improve our knowledge of the orbital parameter, the ephemeris of the asteroid's orbit. And that means that next time when that asteroid is predicted to be somewhere, the error will be smaller because the prediction gets better. So it's a continuous feedback loop of knowledge, predicting the asteroid, doing the measurement, putting that knowledge back into the asteroid's orbital parameters, and then using that in the future to make even better predictions of the asteroid itself. Okay, I'll proceed now. This group is called IOTA, International Occultation Timing Association. So the emphasis here is on the word timing. We do our best to measure the time of the occultation with the most accuracy possible. It's still valuable if you were to just watch the star and note that it did disappear from your location without even measuring the time. That's still a valuable piece of information. It would also be valuable if you told us it didn't disappear from your location. So all of those things are important for amateur citizen scientists to contribute. But the best knowledge is the knowledge that comes from an accurate time of the occultation, both the disappearance and the reappearance of the star. So IOTA provides the predictions of where you need to go and when you need to observe the star to see it predicted disappearance and reappearance. And we encourage that all over the world. Our predictions are available for every continent. And there are IOTA groups. There's an IOTA India group now. It's approximately 10 years old, I believe.
7
years old.
8 years.
7 or 8 years. The IOTA North America has been around for almost 50 years. There are IOTA members in Europe, in Asia, in the Middle East. Very, very big concentration in Japan. They're very active in Japan, and all over the world. Because you only need to be able to observe the star at night from wherever you are. As I mentioned, there's software available, and the software allows you to say, here's where I live, here's how far I'm willing to travel. Now, tell me all of the opportunities in the next 30 days for these occultations, so I can plan my calendar and decide which ones of these I will participate. And once you say in the software, I will participate, everyone on Earth knows you're going to participate, and they know where you say you're going to be. And so, as you'll see here, spreading out the observers across the shadow tells us information about the asteroid that we couldn't get if everyone was all bunched in the same place. And we publish our observations in the Journal of Occultation Astronomy, JOA, in the Journal of Double Star Astronomy, and also in yearly online meetings. We have an online Zoom session for the North America. And there's also, I should mention also, there are quite a few observers in the Southern Hemisphere, in Australia and New Zealand as well. So we really do have global coverage for this. Okay, so we'll move on. Just so you all remember, many of you are amateur astronomers, so you understand where the asteroid belt is. we're talking about this area of space between the orbits of Mars and Jupiter, and we call these the main belt asteroids. And these are the most dense asteroids in our solar system. However, they're not as dense as you might see in a movie like Armageddon or Gravity or any of those movies. You don't have to steer through the asteroid belt. It's still mostly empty space. But there are still tens of millions of these rocky bodies out there. And, it may be that it's Jupiter's gravity that has prevented them from forming another planet. But regardless, there they are, and there are tens of millions of them. And they are relics of the origin of the solar system. So by studying asteroids, we learn about the origin of the solar system, the mechanics that planets were formed, and of course, the actual makeup of the asteroids tells us something about the original material that made up all the planets, and of course the sun as well. So this is an image of an asteroid taken from a telescope here on Earth. Here is a nice close-up image of asteroid Bennu that was taken by the OSIRIS-REx mission, which brought samples of Bennu back to Earth. But of course, to send a mission to the asteroid belt and bring a sample home, or even just bring home photographs of the asteroid, could cost from hundreds of millions to billions of dollars. So it's an expensive way to get the information that you'd like to get. Here's a close-up of Bennu. You can see the sun coming from the lower left here, casting shadows on the surface. You can see here a shadow of a mountain. In fact, you might all remember this mission. Bennu was so rocky that it took the mission planners about a year of going in orbit around Bennu to find one place where it was safe to go down to actually sample the surface without hitting a giant mountain and destroying the spacecraft. There was almost no place on it that was simply an empty, flat place, like a parking spot, where you could safely go down and pick up some rocky dust and go back into space. That's another talk, but I'm sure you're all familiar with that. So we can study asteroids from Earth. We can do it with optical telescopes. We can do it with radio telescopes. Arecibo, before it failed, studied many asteroids, and we could send radio signals up, bounce them back off an asteroid, and actually learn something about its shape using radio. We can learn its orbital parameters by simply observing it. And by observing it over long periods of time, as we see the light from the asteroid dim and brighten and dim and brighten as the asteroid rotates, we can actually tell something about the possible shape of the asteroid that would allow that light curve to exist. But this is a low resolution method of doing this. And of course, it's not, you and I don't have an Arecibo radio dish in our backyard. So we had this opportunity to contribute to solar system science. And this is an example. So on September 13th of 2023, I went out into the desert in my home state of Arizona. And I was told by the software that the shadow of an asteroid called Interamnia would pass across the state of Arizona. And you can see on the diagram, this little red circle that identifies where I went with my friend Paul Fasuna. So the two of us went out into the desert in the evening, set up our telescope. And there were quite a few others from our little group of amateurs in Arizona that also went out and did the same thing in an attempt to measure the occultation of this star by this asteroid. This picture in the background is a screenshot from one of our software tools. There's a Google Earth map in the background showing the ground. The green line represents the prediction of where the center of the asteroid shadow will go, in this case from the upper right to the lower left. The blue lines represent the edges of the shadow. So the size of the asteroid would be from the upper blue line here to the lower blue line here. And the red lines represent how certain we are that the shadow will actually go where it's predicted. In this case, it's a very, very highly accurate prediction. We know exactly where the asteroid's orbit is, and we know exactly where the star's location in the sky is, thanks to the Gaia satellite that has been improving our knowledge of the actual positions of stars in space over the last 5 years. So those red lines are almost next to the blue lines, and this is fairly unusual. It's a very highly accurate prediction. Many times, the red lines might be 5 or 10 asteroid diameters away. And that means that we're not totally certain where the shadow is going to go. So we would spread out much more widely across the desert to try to intercept this shadow, one or two of us. But in this case, everybody knows exactly where the shadow will go. And so we clustered inside what we thought would be the shadow. This is a picture of the telescope that I used. It's got a small camera in the back of the telescope. The output of that camera, it's basically a television security camera. The output of that camera goes into a special box that you see in the lower left here. It's a little black timing box. And the purpose of that box is to take the video signal in and then send it back out unchanged, but with the timestamp from the GPS satellite written on the bottom of every frame of the video image, of the video file. That way, when we go through the video frame by frame and we see the star disappear, we just read off the bottom of the frame the time that happened. And that's accurate to a tenth of a millisecond, 1/10,000th of a second. So highly, highly accurate. So I have here a little, this is a recording of the actual disappearance of the star, and we'll see that come up on the screen here in a moment. Hopefully we'll be able to broadcast that, this live video. So, okay, there we go. So you can see that tiny star there, and as the video goes along, the star has now disappeared behind the asteroid. And for about 15 seconds, we didn't see the star. Now, it's difficult to see that, but that tiny, you can see that tiny dot that got dim, that was the asteroid in front of the star. It was reflecting enough sunlight that we could barely see the asteroid while it was in front of the star. And then as the asteroid moves across and leaves the star, the occultation is over, we can see the star again. And you can see along the bottom of the screen the timestamps to the nearest tenth of a millisecond that we were able to use to analyze that data and measure exactly how long the asteroid disappeared. So when we combine all of the information from all of the observers, not just the ones in the Arizona desert, but also those all over the state of Arizona and other continents as well. Each one of these little colored lines on this picture represents one observer, and their distance north and south here represents their position on Earth, their latitude on Earth. And we're talking here about an asteroid that is, let's see, I think it's about 20 kilometers in diameter. So all of these observers are within a range of about 20 kilometers. But each of these lines has a gap in it. And that gap represents the time for that observer that the star disappeared. And you'll notice that for observers near the middle of the asteroid's shadow, they see the longest occultation. But an observer up near the North Pole or the South Pole of the asteroid would see a shorter occultation because the core diameter across the asteroid up there is a little smaller. And when you put all of that information together, you get, magically, in my mind, an outline of the shape of the asteroid. Now, the picture of the asteroid in the middle here doesn't come from our data. This comes from a group in Czechoslovakia that is doing this light curve analysis. So they measure the change in the light intensity over hours and hours and days as the asteroid rotates and tumbles. And then they do that inverse problem solution. What shape of the asteroid could possibly be and still give this curve, this light curve, as it rotates? So this is one of their models. And when we combine our information about the diameter and size and shape of the asteroid with perhaps multiple potential models of the shape of the asteroid, it's very likely that one of those models will fit our data and the other 2 or 3 possible models don't fit. And so this feedback provides the group in Czechoslovakia and other groups around the country with a way of distinguishing which one of their models is correct and which ones are not correct. They might not be able to identify the most likely model, but with some what we might call ground truth information, we're able to tell them, okay, model number 3 is the one you should probably focus on because models 1 and 2 don't fit this data. And this data is plus or minus 1 kilometer in resolution. There's no way to obtain better data about the size of an asteroid without spending $1 billion and going close up to it and measuring its size with a camera. So price, competitive way, we're way ahead of the game here on Earth, that all of you can do the same thing. And here's an example of that. This is a different asteroid, Egeria. And you see in this case, there were 2 models that the Czechoslovakian group came up with, model 1 on the left and model 2 on the right. And you can clearly see that for model 1, there is a big mismatch circled in red between our data and the model. But if you look at model number 2 on the right, you can see it's almost a perfect fit with the information that we've gotten. And so they would immediately know that model 2 is the model that they should trust the most. And if you were going to send a spacecraft to this asteroid to study it, you would want model 2 to be the shape of the asteroid that you would predict to go there. Asteroid 90 Antiope is actually a binary asteroid. So 2 rocky bodies orbiting a common center of mass. And before our occultation expedition in 2011 to study this asteroid, the best image we had of it was through the Keck telescope. And here's one of those images here. It clearly shows that it's 2 rocky bodies. And in infrared with adaptive optics, it's a little better resolution, but this is still not highly detailed information. But we do know it's a binary asteroid. So in 2011, the IOTA group decided to have our annual meeting in the shadow of this asteroid or near it. And so we had 2 or 3 days of meetings, and then everyone was assigned a particular location, and everyone got in their cars and started driving across the state of California to set up their telescopes and hopefully be in the right place at the right time. So this is the group of people that participated. Unfortunately, I couldn't attend the 2011 occultation IOTA meeting because I was working. Now, thank goodness I'm retired, so I have more time for this. But this is the team that went out for that. And here is a graph of the locations of each of the telescopes that was deployed for this event. Now, many of those people actually set up multiple telescopes in advance of the occultation. So that's why you see many more little telescopes here than you saw people in the picture before. It is possible to set up a telescope, point it and place it in the sky where the occultation will happen, set a laptop to record that event, and then leave it alone in a place maybe behind a tree that nobody will see it, and drive a few kilometers and put a second telescope, and drive a few kilometers and put out a third telescope, and so on. And you can do that as long as you have time. And then once the occultation event time happens, you go back one by one and pick up your equipment. Hopefully it's still there. I've never had any equipment stolen, but we have had cases where coyotes in the desert will come and for some reason tear all the equipment apart. They're mad that it's intruding on their territory. One time I had my equipment stolen by the police. Not stolen, but they didn't know what it was, and so they picked it all up and brought it to the police station, and I had to go and get it out of jail. So that is this is the location, and you can see those little lines on this picture. Each one of those lines represents one possible measurement of the asteroid's shape and diameter. So I've got a little animation here. I hope this comes across okay. So this animation shows what the asteroid's shadow might look like going across Earth. And you can actually see these little blue dots represent the location of the observers. And each time the blue dot disappears, that's because that observer saw that asteroid, that star disappear at that moment. And those two shadows of the asteroids crossed over the state of California like that for about 3 or 4 minutes from the northeast to southwest. And so when we take all of that data from the disappearance and reappearance time and the latitude and longitude of the observer and put it all together, we have we can tell a lot of information about this asteroid. So now remember what our best picture of the asteroid was: 2 tiny fuzzy dots with no resolution at all. Now, not only do we know the shape and size of the asteroids, but as you can see here on the lower component, there's actually a huge crater on the side of that asteroid that no one could ever have known existed until we sent a mission out into space for hundreds of millions of dollars. And now we did this with 20 people and a couple of days of time and a few $100s of gas and motel room charges. So a big benefit there. So we've got many measurements of the asteroid's diameter, but notice this yellow line here. See the little moves up there for folks here in the room. This little yellow line right above the lower component of the asteroid. Maybe if I click on that. It's kind of slow, but you'll see we've got cross sections of the asteroid, but then there's always one line next to the asteroid where no people did not see the star disappear. So that tells you that the asteroid's edge could not project any farther than that, or that person would have seen the star disappear. So we call this a miss or a constraining miss. And that tells you the size of the asteroid in that dimension across the path. The lines tell you the dimensions of the asteroid along the shadow path. But the person who is, yeah, there we go. So now the red dot is on that yellow line. So you can see that just below that, there's a little brown line with a tiny space in it. That is the smallest component of the asteroid blocking that star for the shortest amount of time. But then in the middle, there are actually a few of these lines that one shadow went on one side, one shadow went on the other side, and they did not see the star disappear at all. So they were positioned perfectly between the two shadows, and we give those people a special award for being and we call it the Pillars of Hercules Award, for magically being in between two shadows of a binary asteroid and not seeing an occultation. That's a pretty rare event right there. And you can see the names of all of the people who contributed here along the side. We have 56 observers out there, and 3 of them had these misses in the center. 1, 2, 3, 4. 4 of them had misses in the center like that. So as I mentioned earlier, the closest miss defines the edge of the asteroid in the cross path direction, and that's very important. So when we analyze each one of those observers records a video file, in this case an AVI video file. And when we analyze that video file, we do so with software that measures the amount of light in the star image in each frame of the video. So each dot on this graph represents one frame of the video, and the dot represents how bright was the star in that video frame. You notice the video, the images, the signal is not perfectly smooth. There's always some noise in your signal. And what we try to do is maximize our signal to noise ratio for the best quality data. But the difference is pretty obvious here, that when the star disappears, the light intensity goes down to 0 along the bottom of this curve here, and then immediately climbs back up to its maximum when the star reappears. Now, in this case, this is a different asteroid, Agamemnon, and one of my colleagues, Steve Kennard in Maryland, observed not only the occultation by the main body, but it turned out that this asteroid had its own satellite, a tiny asteroid moon, and just by luck, the asteroid moon was following along on the same path, and after the star reappeared behind the asteroid, and then it disappeared for a few video frames behind the asteroid's moon. That's a pretty unusual and unlikely occurrence, but Steve was very lucky and managed to confirm that this asteroid has its own, at least one, there may be others, but at least one satellite, tiny satellite, and now we know not where it is maybe today, but we know where it was on that day at that time. So with more observations, we could actually confirm the orbital parameters of the satellite in addition to the orbital parameters of the main body of the asteroid. Again, more information we couldn't get without going there. And asteroid Chariklo was actually confirmed, the first asteroid to be confirmed to have rings around it by an occultation measurement that showed not only the main body disappearance, but also 2 dips before and after the main occultation, confirming that this asteroid actually has a ring of debris around it, which partially blocked the light. You'll notice that the light intensity for the ring occultations doesn't go all the way down to 0, because those rings are not solid material. They're rings of some sort of dusty material. Maybe they're permanent rings, or maybe they're just remnants of a recent collision between this asteroid and some other body that ejected some material, which is now orbiting the asteroid. And in a few tens of thousands of years, all that material will end up back on the asteroid. But at the moment, Chariklo has rings around it. So that was a first discovered by amateur occultation. My first experience with occultations was a recording of an occultation by this asteroid called Una, which is number 160. So each asteroid gets a number in the order in which it was discovered. Since large asteroids are easier to see than small ones, the smaller the number, usually the bigger the asteroid. So Ceres, asteroid number 1, enormous asteroid. Chariklo, if we go back here, 10,199, fairly small body asteroid. So the asteroid was observed to occult the star by 1, 2, 3, 4, 6, 7, by nine people, 9 observers. I was one of them. And in the lower left here, you can see our sky plane plot of the asteroid's shape. It matches the predicted shape model very well. But when we analyzed the light intensity in each video frame, we determined that the light didn't disappear all at once. The star's light disappeared in 2 steps. You can see here the red arrows identify the 2 steps in the disappearance of the star. And this was a signal that this was a previously unknown binary star system. And when the asteroid covered 1/2 of this very close binary star system, about half, a little more than half of the light disappeared, which tells you that the first component was the brighter of the 2. It was contributing more light than the other one. And then that disappeared. And as you can see, so here in this picture here, we've got 2 disappearances, 2-step disappearance, and then on the other side, a 2-step reappearance. And so we were able to publish this paper in 2011 as a discovery of a previously unknown binary star. So that was my first official publication as an amateur occultation contributor. I was very proud of that. And it was also my first positive occultation, which turned out to be a discovery of an unknown double star. I don't anticipate that'll ever happen to somebody again to get that lucky, because there are many things that can go wrong with amateur equipment. This was in January in the Northeast. It was snow on the ground. I was wrapped up in a warm jacket. The battery was getting cold. The telescope tracking was starting to fail. Everything was about to fall apart. And I just barely got this data before everything collapsed. And then here it was, a discovery of a double star. So you just never know. You go out, you roll the dice, and you hope they come up good numbers. This is a picture of the video time inserter device that we talk about. So by taking the video signal from the camera, putting it through this device, which has its own GPS antenna inside the case, it is constantly receiving signals from multiple GPS satellites. It knows what the time is to the nearest microsecond, and we put that accurate timestamp on each frame of video. So that is a permanent part of the record of the occultation. And there's no question then about when did the disappearance and reappearance occur. These are some of the cameras that we use. These are small security cameras, analog video cameras. I will say that today, now this is several years old, today we've also got the opportunity to use more traditional digital astro imaging cameras by SBIG and ZWO, the ASI series of cameras. And those cameras take digital images. The digital image cannot be processed by our IOTA video time inserter analog processor box. And so we've had to come up with new techniques for time-stamping digital images, where each image, instead of being a frame of a video, is a separate FITS file of its own. And you have a series of FITS files that make up what used to be a video file. And now it's a series of individual digital frames. The challenge is to put a timestamp, not the Windows timestamp when it was written to disk, because we never know when that could happen. We're talking about the timestamp when the image was actually acquired by the camera. That's the important timestamp that we want. We never trust the timestamp on the computer as being the accurate time. We always have to use an independent source of timestamp. Yes. And this is one of the small analog video cameras that we use. This one is made by a company called RunCam. Does anyone have a drone? Small, drone device? Well, many drone flyers will try to do first-person video by putting a small video camera in the drone, and then you wear a pair of goggles and you fly the drone as if you were a pilot sitting in the cockpit of an airplane. So these little tiny cameras we found were very sensitive to low light and were very cheap. So we bought 100 of them and sold them at our cost to amateurs like yourselves who wanted to begin this hobby without having to spend $700 or $1,000 on a fancy digital astro imaging camera. And we've got hundreds of these out in the field now being used by amateurs. And we always put a little focal reducer on that to increase the field of view and to make the star images a little smaller and brighter. That improves the signal to noise ratio as well. You might ask, how big does the telescope have to be to do this work? Well, it depends on the star brightness. The only requirement is that you should be able to see the star on your recording before it disappears. So if the star is bright enough, for that Antiope occultation, the star was magnitude 7. And so the size telescope we needed was, as you see here in the lower left, it's half of a pair of binoculars. We bought some cheap binoculars on eBay and unscrewed the lenses, and each one became a telescope. Just put a camera in the back of the binocular lens, and you have a telescope. Put it on a tiny tripod, set it down in the field, aim it at the right place in the sky, and then do that again and again and again. Because the field of view with that very short focal length lens was about 3 degrees of the sky, no one had to point their telescope very accurately. And of course, at a magnitude 7 star with a highly sensitive camera, it was easy to see that star. Now, if the asteroid is predicted to occult a star of magnitude 10, let's say, then you would need a larger telescope in order to see the star before the occultation. And if you went down to a magnitude 12 star, instead of a 120 millimeter telescope, you might need a 200 millimeter or 250 millimeter aperture just to see the star. It all depends on the brightness of the star. And since there are many more faint stars in the sky than there are bright stars, most of the occultations that are predicted for you will be faint stars. And so it's a question of, if you can't, if you don't have a 250 millimeter or 300 millimeter telescope, you wouldn't even try magnitude 12, 13 occultations because you wouldn't be able to see the star. But if the star is a little brighter, then that's a good candidate for you. And over time, you learn what's the faintest star I can see with my equipment. Now, of course, if the star is high in the sky, that's great. But if the star is 12 degrees above the horizon, you lose a magnitude or two just from atmospheric interference. So there's that question as well. So always something to think about. You can also manually time these events with a stopwatch. Or with a tape recorder, listening to the beeps from a radio station that broadcasts time, like WWV, beep, 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 once every second. If you record that, and then when the star disappears, you say out, and when the star reappears, you say in. Then later on, you can go back and analyze the audio recording and get a time recording of the occultation. And this is how IOTA members did all of their occultations for many years using audio recording until just before I started getting involved in this in 2010 or so. Video recording came along, and we were using not laptops, but as you can see once the screen comes up here, digital video tape recorders, little DV tape recorders down in the lower right. You can see one of those, a little Canon digital video recorder. So the analog signal was recorded onto a digital tape, and then we would extract that by rewind the tape, push play, and record that into the laptop to do the analysis of the video signal. Now we can eliminate that step by recording directly to the hard drive or the solid state drive of a laptop. So I've given away all of my little tape recorders, and they were 20 years old, and they usually would fail, and they didn't work well in the cold. And sometimes the tape recorder heads were they had two heads on them, and sometimes one whole set of heads would fail. And so you would get a zebra stripe, like the stripes on the back of your chair here. And you would hope that the star was actually in the one that worked, but sometimes it was in the one that didn't work. And that was frustrating too. So I was very happy to eliminate the tape recorders from all of that. So there's all this timing. So I mentioned digital. We about a year ago, a very smart man in Canada, Mark Simpson, came up with a design for a Raspberry Pi based digital data acquisition, which he calls ASTRID, Astronomy Imaging Device. And the ASTRID device has software in it that can do a plate solve of a picture of the sky and know where it's pointing. And then it can also send commands to a telescope mount that has a go-to capability. And it can go find a particular star and then do another plate solve photograph and see if it's close and make small movements. So we can iterate and focus in on the star. And then if your telescope can track the star, it'll keep tracking that star until the occultation occurs, and it can automatically record that occultation onto the USB drive. And then when you go out, pick it up, you have your data ready to analyze in your laptop. So Astrid is a real breakthrough. It's digital. It uses GPS, an external GPS antenna to obtain the timestamps. And it has the ability, as I said, to do plate solving and to control telescopes of many makes and models, Meads, Celestron, Skywatcher, etc. And it can also do something to help you find the occultation, and that's what we call pre-pointing your telescope. So if you were to look at a particular star in the sky, an hour later, that star would be in a different place in the sky because the Earth has been turning. Well, that means that if you were to point your camera at a place in the sky, eventually along that same line of declination, eventually that star would drift through your camera field of view and would come in the left side, drift across the field, and disappear out the right side. So if you can point your telescope at a place in the sky where that star will be at the moment it's predicted to be occulted by the asteroid, you can, as you saw in my interamnia video, that star was drifting across the screen, and when it got right near the middle of the screen, it disappeared. So what I had done was I pointed my telescope at the place in the sky very far from where the star was, about 2.5 hours before that, and then I just sat back and waited for the Earth to turn my telescope until it was pointing at the star. And at the right time, as long as you point your telescope at the right time, at the right place in the sky, then you can turn off all the tracking, you can forget about batteries, you can forget about temperature. The Earth turns at the same speed. It doesn't require batteries. It doesn't care that it's cold outside. You can't kick you can still kick the leg of the tripod, and that's a mistake. So, once you get this thing pre-pointed, just get away from your equipment and leave it alone. If you do use a tracking telescope, you can tell the telescope to point to this place in the sky, and at the right time, you simply turn off the power of your mount, and now you wait for the Earth to turn your telescope to the star that's going to be occulted. So pre-pointing is much more reliable. You'll have much more hair. You won't be pulling your hair out with all the problems with all of your equipment. It's a fantastic way to do this thing. And Astrid can help you pre-point the telescope. Normally, to pre-point your telescope, you have to find a kind of a bright star somewhere along that line that the target star will be drifting. And there isn't always a bright star close to that line. So if you find a bright star, now you have to sort of star hop your way up or down to some tiny field of faint stars and hope you're in the right place. But Astrid does a plate solve. So it will, if you point it at a field of faint stars and it does a plate solve, it says, okay, you're pointed on you're on the right line of declination where the target star is going to be. Turn off the power, everything's fine. So it eliminates the need for manually finding a bright star near the pre-point line for that particular event, and that's very convenient. So the software tools that we have, I mentioned, we've got the analog tools, the analog program that records NTSC or PAL video. Been using that now for 20 years. There's a software called Occult4, which is a very powerful program. And Occult4 is the program that can take locations of 1 million stars and the locations of 100,000 asteroids and calculate whether any combination of those two will cause an occultation where you live for the next 30 days. And it does it like that fast. And I have no idea how it can be that fast, but it's amazing. And Occult 4 runs in the background behind the other easy to use software that we call Occult Watcher. Occult Watcher would run on your computer desktop, and that's the program you would say, here's my latitude and longitude where I live, here's how faint a star I can see in my equipment, and here's how far I'm willing to travel. So take all the millions of possible candidate occultations from the whole globe and throw away everyone that doesn't meet my filter and only show me 50 or 100 over the next month that I have candidates, and then I'll decide which ones of those I'm interested in. And sometimes the scientists will ask IOTA, hey, we've got a mission going to a particular asteroid. We're very interested in occultations by that asteroid. So if you could all please try to observe an event by that asteroid on this day of this star, we would really appreciate it. And then many more people will sign up when we have an invitation like that to help the mission do something very useful. And then there's also software using that analyzes the video files and extracts those times, and then we report those times to the Minor Planet Center, and the information about the asteroid orbit and size and shape becomes part of the official database of information about that asteroid in the Minor Planet Center data set. And then when a scientist is interested in knowing something about that asteroid, they go to that database and they find not only information from the Arecibo information from years ago, but also information from IOTA members who have made these contributions. And that's what we invite all of you to participate in, is the gathering of useful scientific information for scientists who are interested in learning more about the origins of the solar system, the dynamics of the asteroid belt. You might recall Jupiter being hit by a comet, Shoemaker-Levy, all kinds of interesting things going on out there in the asteroid belt as well. And in April of every year in New York State, there's a big, I guess you would call it a trade show called Northeast Astronomy Forum. And for the last 7 or 8 years, IOTA has had a booth in at NEAF. They give us the space for free. We're a nonprofit, and we do this for educational purposes, because in this giant room, I don't have a picture of it, but there are 500 of these booths, mostly filled with people trying to sell you new equipment and new telescopes and new cameras and new mounts. And the Celestron is there. When Meade and Orion were in business, they were there, and every vendor of every possible thing, including the little yellow rubber caps that you put on your eyepiece to keep the dust away. You can buy those, by the dozens, and so every size dust cap is available by some guy who that's all he does, makes dust caps, right? So we're there to say to people, hey, you can do some scientific work with equipment you already own. So come and see our booth. We've got all the software running. We've made these posters that we put on the back wall. There's little examples of telescopes and things here. And we even had a little blinking LED light up on the far wall of this happens in the gymnasium of a community college. So we put a tiny LED with a timer circuit blinking on and off, and we invite people to make their own recording of an occultation and then analyze the data right there on one of the laptops. So people had fun doing that. We could demonstrate how that worked as well. So I think that's all I have. We've got a website, occultations.org. That is the North America IOTA website. There's also an IOTA India website that I'm sure all of you are aware of. The software is available for free to download on our website. We have a chat list on groups.io, IOTA Occultations on the groups.io website. You're welcome to join that. It's very active, and you can ask questions there. And with that, I will thank you and invite your comments and questions today, and we're welcome to have a discussion. So thank you.
Yes.
Questions, comments are welcome. I'd like to also inform that we've had about 12 people watching online. Hello to them as well.
Very good.
Even they can ask questions. If you're watching on YouTube, you can put your questions in the comments as well.
So how many times you actually the prediction went wrong? Sometimes you did some prediction was there for 30 seconds, but you got only for 20 seconds. Even at the central line, or maybe sometimes you got 40 seconds, 50 seconds at the speed. So what is your experience?
As far as the accuracy of the predictions, before the Gaia missions, there was quite a bit of uncertainty in the position, the actual position of many stars. And there's also uncertainty in the position of the asteroid. And in order to do a prediction of the shadow on Earth, you have to multiply the error in the star position by the error in the asteroid position. And the result is that you have really very little idea where the shadow will be on Earth. Now, the Gaia satellite is providing us with extremely accurate positions of millions of stars, and it also is able to give us accurate positions of thousands of asteroids as well. So the error in the star position has gotten much smaller. The error in the asteroid position has gotten much smaller. So now we're multiplying two very small numbers together, and that's how we can be fairly confident that when we go out, if we think we're in the shadow of the asteroid, we very likely will be. So things have gotten much better in the last 2 or 3 years, to the point now where my prediction feed at home, even with all the filtering that I do, I have hundreds and hundreds of candidate occultations to choose from my own backyard, from my observatory in my backyard. And because I have a 14-inch telescope in the dome, so we can see very faint stars, and the number of possible things I could stay up all night, every night, and never sleep, and just record these occultations, and probably most of them would be positives. But I like my sleep, so I don't do that. I just pick and choose. But so yeah, the improvement in the accuracy now is much more encouraging. So that you don't have to go out and for the first 20 times you go out into the field, you see nothing happen. We want you to have some successes quickly. And these days with the Gaia data, we can tell you you're likely to have a positive fairly soon in your career as an occultation observer. Thanks.
How much is the possibility of it going wrong in prediction because of rotation of because earlier observations may be in one position. When it is coming again in front of some other star, it might have turned and then dimensions are different.
Absolutely. So the question is, what is if the asteroid is not spherical? There's one asteroid, Calliope, that looks like a dog bone. It's elongated and big at both ends. And if the asteroid is pointing at you end on, it looks much smaller than when it's sideways. And so we don't know exactly what position it will be in the orbit. It might only take 5 minutes for the shadow of that asteroid to cross the whole planet Earth, whereas the orbital period of the asteroid could be many hours. So there's no rotational change in the asteroid's position in the sky during the occultation. Whatever position it's in, that's what everybody sees. And if it's coming across the long way, then great, everybody will have an occultation. But if it's coming this way, then only a few people in the middle will. And there is some knowledge about the orbital, the actual position angle of the asteroid, but it's not as accurate as the time that it will come. So yes, it's very likely that for a elongated or binary asteroid, you could predict a positive, and have many people have misses because the orientation of the asteroid is just the worst possible orientation for the size of the shadow. That's definitely possible. Yes, sir.
So
Yeah, let's microphone so I can hear. I might need some help.
so when which is operating the star, it's also operating at the moment when it's when the orientation is happening. Yes, that's
No, typically the asteroid rotation period would be many hours or days, but the occultation would only last a few seconds. So there's no rotational change in the asteroid's position as it moves, as its shadow moves across Earth. It would be fixed, almost fixed. If the asteroid was rotating that fast, it would probably already have fallen apart. So the answer is we don't expect any change in the asteroid's shape in the sky during the occultation. Later on, an hour later, it might be a different orientation, but it's already over by then.
so what is the error bar of
A little closer. Sorry.
so what is the error bar of the atmospheric effects on the measurements?
What is, sorry.
So
The effects of the atmosphere.
atmosphere.
So yeah, well, one effect I mentioned is if the star happens to be low in the sky, then some of its light is blocked by the atmosphere and dust and dirt and clouds. So you need a bigger telescope to see the event. But the most important effect is turbulence. The turbulence will cause the star to flicker or twinkle, and as a result, the light curve before and after the occultation is much more noisy than it would be if the star was high in the sky. You might get a small amount of flickering, but not a lot. And so if you have a occultation of a very faint star, then the drop in the light could be very small. And if the signal is so noisy that you can't really tell that you had an occultation in your light curve, the effect of the atmosphere is to remove all the possibility of getting any scientific information from that event. So that the more turbulent the atmosphere is, the lower the star is in the sky. All of those things work against you, and also the drop in light. So if the asteroid is very bright and the star is very dim, as the asteroid approaches the star, the two sources of light merge and become one, as far as your telescope is concerned. And then when the asteroid goes in front of the starlight disappears. But if most of the light was coming from reflected light from the asteroid in the first place, then when the star disappears, almost nothing changes. And so the worst combination is a bright asteroid like Ceres occulting a very faint star. You would see almost no difference in the light when the star disappears from when it comes back out the other side. And that's the big. So sometimes you get those combinations, and those are the most difficult for the analysis after the fact, to try to have some sort of statistical prediction, some confidence that you actually saw the event and when did it happen. Now we know everything we need to know about the asteroid series, so it's not important that we get information from occultations about Ceres, but there are other asteroids that are fairly bright, and when they occult very dim stars, the signal drop is very small. And so if the atmosphere is turbulent, the drop in the signal is lost in the noise from the turbulence, and you have a poor signal to noise ratio. So we like to have a signal to noise ratio of about 5 or more. to be confident that we're actually seeing something in the data. But we'll take whatever we can get. It's just that there's more uncertainty in the prediction of the time if the signal to noise ratio is low.
So how IOTA gets its database? Means how IOTA predicts the occultation?
How does IOTA predict occultations? There's the program that I called Occult4 is written by a fellow in Australia named Dave Harold. And Dave Harold, I'll say it to the world, is a genius. And he has implemented software that can do those combinations, those predictions for every star that's available in the database, for every asteroid, and for every place on Earth, and for all time in the past and in the future. So Occult4 is the engine that does all of our predictions. And then the job of the software on your desktop is just to throw away all those predictions that don't apply to your position or your equipment. So that's the filtering process that goes on in the desktop program that you would run on your machine, Windows or Mac. And then, so thank you to Dave Harold for writing that program and maintaining it, and being and being as careful as he is with our data. In the JPL databases, the Minor Planet Center databases, our measurements of asteroid diameters are considered to be the most accurate of any source of information from any observatory on the planet, other than sending a satellite to the asteroid to measure it itself. So we have a very high reputation among the scientists who use our data. And before your measurement result is entered into the database, it's checked by volunteers in IOTA 5 or 6 times for accuracy and consistency and confidence before it goes into the database, because of a measurement that's in error that makes it into the database contributes in a negative way to the prediction knowledge about the asteroid's orbit. And now the next time we make a prediction of the asteroid's orbit and we use a bad piece of data, we're going to think the asteroid is going to be here when in fact it's here, and suddenly we've lost it from our ability to find it again. So there's a whole set of very serious checking that goes on. It can take up to a year for your measurement data to show up in the JPL database, because it takes that long for the 8 volunteer checkers who are getting 25 of these events per day from all over the world, and it takes them 10 or 12 hours for each one. You can see we have a big bottleneck right now in the North American pipeline just to be able to confirm these measurements. But it's important that no data ever be entered into the database without it being as accurate as possible. Yes?
If we observe any partial occultation, so that asteroid does not occult the star fully but only partially.
So, good question. The question is, do we see partial occultations? Well, for most stars, we consider the star to be an infinitely small point of light. But that's not true for every star. Betelgeuse, for example, has an apparent diameter that can be measured and seen. And last year, there was an occultation of Betelgeuse by an asteroid whose size was smaller than the size of Betelgeuse. And so it was sort of like an annular eclipse, if you want to consider it that way. And so the light from Betelgeuse didn't disappear completely and went down to a level, I forget, it was maybe half, and then back up again. And it didn't disappear instantly like this. It disappeared gradually as the asteroid went across it, and then there was a flat bottom, and then it came up gradually on the other side. So that can happen, but only when the star has a real apparent diameter that we can measure from here on Earth. There's other level things like Fresnel diffraction that can affect the edges of asteroids, but typically you don't have to worry about that. You might, however, if you were very lucky, observe a star disappear once or twice in case the asteroid had like mountains on it, and you saw the star disappear behind the mountain and then reappear in the valley for an instant and then go behind a mountain and then come out. How many of you have heard about a thing called a lunar graze? Well, before, yeah, folks here have actually done those. At the north and south poles of the moon, before we had the Lunar Reconnaissance Orbiter measurements and the LOLA laser measurements of the entire surface of the moon, we knew a lot about the equatorial areas of the moon, but very little about the polar regions. But we could learn something about the geography of the polar regions if the moon, as it went through the sky, was passing in front of a bright star and you were in just the right place on Earth. You could see the star disappear and reappear and disappear and reappear behind the mountains and the valleys on the moon. And if multiple observers did that, you could actually draw the geography of the north and south poles of the moon by timing these graze events. And you could have multiple, 10, 15, 20 of these events in a minute as the moon went in front of the star, if you were in just the right place at just the right time. You can still do these. There's no scientific value in these anymore because we know the entire moon's surface accurately to within a few centimeters. But it's fascinating. I've been in the field and watched this. It's so exciting to see that star disappear, and then all of a sudden it comes back and goes away, and comes back and goes away, comes back and goes away, multiple times. And you're just imagining in your mind that here are these mountains on the moon that you have no idea they're there, and yet they're tall enough that you can actually measure their height from Earth just by watching a little star go behind the mountain range on the moon. So it's really exciting to do that. And we also make graze predictions as well, in case you ever want to go out and do a graze, the lunar graze. We'll tell you exactly where to stand and where to watch it. And even in a pair of binoculars, it's a fascinating thing to see. Because typically, if it's a really bright star, it's easy to see in a pair of binoculars, not naked eye, but just a pair of binoculars or a small telescope. It's very exciting.
What we'll do is to limit the questions because I think we should also have a useful interaction on action points that we have. And of course, we are getting so many insights and there are so many variations of things that can be done with asteroid occultations. And he even mentioned lunar occultations, some of which were actually used by radio astronomers way back when the Hootie radio telescope came up. That most of the observations there gave amazing details of radio checks, previously never found, but they were done with lunar occultations. There's so much to do. I'm still, as I said, that we would like to end with some action points that we could have. Let's also make connections with IOTA and IOTA India. That if any of you have got inspired, excited by this interaction, you could start contributing with your own small telescopes and small things, small equipment. Also, there's a lot of scope for software, as you saw, software and hardware development in this. So, let's have that chat as well. We'll end the question answering.
So, as you mentioned before, there is this asteroid imaging device. It is used to predict timing or occultation events. So, how basically it works? That was my question. What is the approach and how Raspberry Pi being involved in the data acquisition part and stuff?
So, asteroid is it's a combination of a Raspberry Pi small computer and a special board that can interface to a camera. So they're stacked together, camera, GPS board, Raspberry Pi, all in one case. And one of the boards on the Raspberry Pi has the ability to have the GPS signal come in. And so the combination of hardware and software lets the asteroid take a picture of the sky and then insert into the FITS file header the exact microsecond that the picture was taken. and then write that through the Raspberry Pi computer to a USB stick that's coming out the side. And you would interface, talk to the raster device through VNC software. There's a VNC server program running on the Raspberry Pi, and you would install the VNC viewer or client on a laptop or an iPad and connect. And the Astrid broadcasts a Wi-Fi hotspot that you can connect to, just like the current modern these mounts like C-Star and EVScope. They broadcast a Wi-Fi hotspot. So you would connect to the hotspot from your tablet or your laptop. Use the VNC client to bring up the Astrid desktop, and now you can interface with Astrid, start the apps running, tell it which event you're interested in, and then say to it, okay, now please control my telescope, and it would send the commands through the USB cable to the telescope. So all of that would be done through some sort of desktop interface that you had, either a laptop or an iPad. And all you need to do is have a battery, a power supply, 12-volt power supply for Astrid, and that's powerful enough to last for as long as this occultation event might be. It might be several hours, so you would want a nice sturdy battery, maybe 10, 15 amp hour, 12-volt battery, and that's all you need.
So, thank you all for your questions. So, before we proceed with the discussions, we'd like to show you the IOTA India website. So, if you want to enroll or become a member, you can visit the IOTA India website, which is iota-india.in. And then you can fill out a form. You can click on join here, and then you can fill out a form and become a member. So what happens when you become a member is you